The goal of the study is to assess anthropogenic warming's influence on the risk of extreme wildfire behavior in California using an empirical approach where the relationship between temperature and the risk of extreme wildfire behavior is learned from the data. The extreme wildfire behavior that we focus on is extreme daily growth, specifically 10,000 acres or more in a single day. Since we are specifically interested in the occurrence of these extreme events taking place or not, we convert our wildfire data into a binary, indicating if growth above 10,000 acres occurred or not. This is our response variable. And specifically, this is 17,910 geographically dispersed fire days in California from 2003 to 2020. We also acknowledge that there is inherent stochasticity and thus uncertainty in the possibility of extreme daily growth occurring for any given fire day. Thus, rather than focus on discrete binary predictions of extreme growth occurring, we focus on how warming has influenced the risk or probability of extreme daily growth. Now, we are interested in how a fire's environment, including ambient temperature, influences the risk of extreme daily growth. So we set up a regression problem with a number of predictor variables established to be important influences on wildfire behavior. These predictor variables represent fundamental components of the well-known wildfire behavior triangle, which has edges of topography, fuels, and weather. Many traditional regression methods assume that the influence of any predictor variable is independent of the influence of other predictor variables, and that their influences are monotonic, if not linear. However, it is well known that the influence of any one of these predictor variables will be highly conditional on the state of other predictor variables. Thus, rather than use traditional regression methods, we use machine learning models, specifically neural networks and random forests, in order to estimate the associations between the environmental conditions, or predictors, and the risk of extreme daily wildfire growth. These models are able to account for nonlinear, non-monotonic, and interactive relationships between the predictors. We confirm that these predictors do constrain the risk of extreme wildfire growth using cross-validation on 3-year chunks. Each 3-year chunk is held out in sequence, and the remaining data is used to train the machine learning models. Then the machine learning models make probabilistic predictions of extreme growth on the held out data, and scoring metrics are calculated. We use 4 different scoring metrics to assess model performance and normalize them against a naive model that always predicts the baseline frequency of extreme growth. We test 1,000 neural network configurations by randomly varying hyperparameters and 1,000 random forest configurations also by randomly varying hyperparameters. Our main reported results are results that are averaged over the top 10% of models in this cross-validation test. All of these models do much better than the naive model. Because the learned relationships are associational, they cannot strictly be considered causal, though knowledge of the physical world, for example, that fuels burn more readily when they are drier, can be used to supplement these associations and infer causality in certain circumstances with decent confidence. So our overall approach consists of 2 broad steps. 1 is learn relationships between environmental variables and the risk of extreme daily fire growth, assuming an active fire. And 2, recalculate the risk under altered background climatological temperatures associated with anthropogenic warming. And then we compare these 2 calculated risks. The altered background climatological temperatures come from multi-decadal and multi-model means produced from global climate models. These climatological changes are a function of space and month of the year. Now, it is already well established that anthropogenic warming's influence on wildfire behavior is not primarily via temperature itself, but rather through temperature's influence on aridity. So when we are attempting to assess anthropogenic warming's influence on the risk of extreme wildfire behavior, we would be left with a large underestimate if we did not also consider temperature's influence on aridity predictors that have a direct relationship with temperature. Thus, we also propagate changes in temperature into 3 other predictor variables, specifically the daily mean vapor pressure deficit, which influences the aridity of fine fuels, 100-hour dead fuel moisture, and 1,000-hour dead fuel moisture, which represent fuel moistures for fuels of different sizes and thus different response times. Both of these dead fuel moisture variables experience the change in temperature over an entire 125 days prior to the fire day. So we have the original values of the environmental predictor variables, and we have altered values corresponding to background climatological temperature changes. Everything else, topography, vegetation characteristics, precipitation, wind, and absolute moisture content of the atmosphere, is held constant. We believe this is a conservative approach, as there is evidence that most of the predictors that are held constant here are likely being pushed in a direction that would exacerbate rather than mitigate the risk of extreme wildfire growth. Our approach is similar to the existing pseudo-global warming or storyline approaches in the extreme event attribution literature, which also hold almost everything about a given weather event constant except for a small handful of variables of interest. The difference, however, is that in the pseudo-global warming or storyline approaches, the influence of the independent variable, temperature for example, on the extreme weather event is typically quantified through a physical or mechanistic model that calculates interactions through a conglomeration of physical equations and semi-empirical parameterizations. Our approach is similar in principle, but the models that quantify the influence of the independent variable on the extreme event are machine learning models that have learned the empirical relationships directly from the data. So with the altered predictor values, the pre-trained machine learning models can then make altered predictions of the probability of extreme daily growth on the same historical fire days, but under different background climatological temperatures. In our procedure, the out-of-training sample predictions and shifts in future probability are calculated at the same time, so the models never have access to predictor information for any fire day that they are making a prediction for, either using original or altered predictor values. Our primary results compare the probabilities of extreme daily growth calculated with the original predictor values to those calculated with the altered predictor values using a probability ratio. A probability ratio of 1.5, for example, would mean that the climatological temperature change being considered made the risk of extreme daily growth 50% more likely. Also, for historical fire days that did see extreme daily growth, we can calculate the fraction of the risk of that occurring that was due to anthropogenic temperature change. Due to the output of our method being fundamentally probabilistic and due to its conceptual similarity to the storyline approach, we refer to our method as the probabilistic storyline approach for extreme event attribution.